Hi there. My name's Jared, and I'm a computer engineer. That's what I studied in college. I'm currently studying for my master's degree in computer engineering as well. I'm a full time software engineer. I do everything from data analysis to software development and test automation. So I've done a little bit of everything. And today we're going to be taking a look at Shenzen I. This is a game by Zachtronics. They make some excellent automation and programming type games. Um, you may have heard of some of their other games like Opus Magnum. Really excellent sort of puzzle games. So I'm excited to get into Shenzen I. This is based around assembly programming. I have some experience doing assembly programming back in my studies. So hopefully, I should be able to explain some of the concepts we'll see in this game. One cool thing about this game is that actually they give you these data sheets here, so you have to pull up an actual document that has all the instructions for how the different components work inside of the game. So it's really cool. They give you this document. There's some story stuff in here, but also like diagrams and like how their programming language works in here. So we're definitely going to have to reference this document throughout the gameplay. So we'll get back into it and let's get started. Welcome. Dear new employee, thank you for joining Shenzhen Longteng Electronics Company. We aim to become a world-leading company in the electronics industry and a respected brand with products in homes, offices, and public spaces across the world. Diligence, connections, and salubriousness are the main principles here. So it looks like we got some backstory here. You're welcome to read this, but I think I'm going to get into the game. Important, read the manual. Know you're good at engineering, but you're going to need the manual. Okay, well, I've got the manual pulled up and we will reference it whenever we need to. Product, fake surveillance camera. Create a working design to view histograms and leaderboards. This product is an imitation security camera. It has two blinking lights. The first light blinks in a regular pattern. The second light is an internet light, so it should blink in a more random pattern. As you will notice, the design is partially complete already. A previous engineer left before finishing. Note the timing diagrams in the verification tab. When you simulate, your outputs should match those expected values as indicated. All right, let's go ahead and get into the first design here. Fake surveillance camera. Okay, so I can show or hide the components here with tab. Looks like I can drag this around, part not on board. So I guess I got to keep it within this grid area here. Looks like I can draw wires. And it said something about the verification tab. So if I go to this verification tab here, I guess I can see what I need to do. So we have two things here, active and network, simple outputs. So it seems like I need to get the outputs to match these two patterns here. So what happens if I just run this right now? So I got step, advance, and simulate. So step. Okay, it looks like it goes each one of these color-coded bars is like a different step in the simulation. So I can step through it and see what happens. And we can actually see highlighted up here on this microchip, we can see where it's at in the instruction. So I can advance, advance, advance. Okay, so it looks like the top component is working because our output, I assume this is the output here, is matching the diagram down here. But it looks like this at the bottom, this is not working here. So if I simulate all the way, we can see that, yeah. So this top one is good to go, but this bottom one isn't. So let's see what's actually happening here in order to generate this output. We're working with assembly code here, or this game's version of assembly. And in assembly programming, all of your instructions like your code is very low level. So you're doing very basic operations. You move a value here, you add it, you subtract a value, you move it to a different location. So it's very basic operations. So what we can see here is that the first instruction is, first, let me reset. Move 0 P0. Okay, so we got P0 right here. It looks like that's one of our outputs. Then move 100 P0. So I guess that's, we're setting the value of this output from 0 to 100. And then SLP, I presume that's sleep for 6 ticks, I guess. So let's see, and I guess that would match up here, right? So we move 0, so the signal is low, expected 0, for 6 ticks, sleep 6, then move 100 P0, and then sleep 6. And then I guess this will just loop over and over. Yeah, it looks like it just loops over and over. So let's I think we can try this here. We'll do something very similar for this network output here. So it looks like we sleep for 4. Well, first we're going to start by moving 0 to this output P0, which is then going to go into this network sync here, this output, which will actually output this signal. Move 0 P0, then we're going to move 100 for 2 ticks. Well, we need to sleep for 4 ticks, then move 100 to P0, sleep for 2 ticks, move 0 P0, sleep 1 maybe, and then move 100 P0, sleep 1, and then that should be it, I think. Let's see what happens. Let's just step through it. So we're sleeping 2 now, then we set it back down to 0, then we set it to 100, then we set it back to 0. So it looks like we got the pattern right here. So let's go ahead and simulate the rest of this. All right, and we've completed one test run, and we have to let it run a little bit longer to make sure we really got it. All right, and I guess this is our results screen here. So production cost, power usage, and lines of code. We have what looks like histograms here and like a leaderboard. So we can, I guess, compare against our friends to see how our solution stacks up in terms of these 3 categories. So each component up here has a price. So whoever has the cheapest solution or the most power efficient solution or the fewest lines of code. Okay, that's pretty cool. All right, so that's the first problem solved. Let's go back out to our email and see what else we got here. All right, replacement factory module. Our factory floor has some examples of older equipment that require control signals to be amplified. We had a device to adjust signals for this type of machine, but recently it was broken. This is an appropriate project to teach you about inputs. Okay. All right, let's check it out. All right, so we have control in and control out. Let's see, control in is a simple input connected to factory equipment. Control out is a simple output connected to other factory equipment. The signal from control in should be multiplied by 2 and copied to control out. So all we're doing is copying or multiplying by 2 and copying it out. Okay, so we just amplify the signal. Okay, well, let's go ahead and grab one of our little circuit boards here. Pin type mismatch. So I guess let's try P0. So P0 works, but not X0. So I guess the ones with the little triangles on them, we can't connect these two. Okay, well, so that should work. I presume this wouldn't work. Yeah, that doesn't work. All right, so we're going to go into P0 and we're going to go out of P1. So we're going to get a signal coming into P0. And if you go look at this documentation sheet here, so here's our microcontroller here. Let's see if we can figure out what's going on with these inputs and outputs. So this is the MC4000. That's the one we're currently using, the MC4000. That's our microcontroller. So it has 9 lines of program memory, 1 general purpose register, which is going to be the accumulator here, 2 X-bus pins, and 2 simple I/O pins. So it looks like P0 and P1 are the simple I/O, and X-bus is X0 and X1. Okay, so we have different types of interfaces here. So I guess what we're doing right now with this factory equipment is just going to be a simple analog input-output, which is why we have to use those inputs and outputs. Okay, so let's see if we can figure out how to copy from P0 to P1. Okay, so we need to find some information about the instruction set here. Basic instructions, here we go. NOP, instructions no effect. That stands for like no operation. So NOPs are used to essentially waste a clock cycle. We got move, copy the value of the first operand into the second operand. We've got jump commands, so that'll let us jump to a specific line of code. We've got sleep, then we've got SLX, sleep until data is available to be read on the XBus pin. Okay, so we've got 2 sleep commands. One just sleeps for a determined amount of time, and the other one sleeps until data is ready on an XBus pin. And then we're also going to need to multiply, so let's look at these arithmetic instructions. We've got add, subtract, multiply, not, isolate the specified digit of the value in the register. Okay, interesting. So it's like a selection. So like this selects the first bit, or the first digit rather, and then DST, set the digit specified with the first operand to the value of the second operand. Okay, interesting. But right now all we need to do is look at this and multiply. So let's go back over here. So we should be able to say multiply P0 P1. Does that work? Multiply the first value, multiply the value of the first operand by the value of the accumulator register. Oh, okay. And store the result in the accumulator. So what I think we're going to have to do is, we could do this one of 2 ways. We could move the value of P0 into the accumulator and then multiply by 2, which should store the result in the accumulator, and then we can move accumulator to P1. So this should take the input, move it into the accumulator register. A register, by the way, is just a place in computer memory that stores a value. So these are going to be the lowest level memory storage that your computer has access to. So your CPU, it only has a few of these registers. In this case, we only have 1 register, which is the accumulator, but this is the fastest data storage, you could say, that is in a computer. So whenever you're doing, your CPU is doing very fast math operations, it's going to be moving values in and out of these registers very frequently. But, all right, this should work. Let's try this. Part not sleeping. Oh, interesting. Okay, so we have to sleep. Let's try to just sleep for 1 then. Okay, looks like so far this is working. Let's go ahead and simulate. All right, and it looks like that successfully worked. Now, I want to show you, there is another way that we could do this too. We could, instead, we could move 2 into the accumulator and multiply by P0. And this should work as well. So if we step through, what we see is going to happen. So it hits the first command, move to the accumulator, and we get a 2 in the register. Next up, we're going to multiply by the value of P0, which in this case is 25. And it's going to move the result of that multiplication. So it takes 2 times 25, puts that in the accumulator here, and then we take the result of that and move it out into our output bus here, into P1. So this should also work. So either solution is valid. All right, sweet. All right, next up, please enjoy a game. Win a game of solitaire. What? Huh. There's solid. Oh, we've got solitaire now. As much as I like solitaire, I think I will save that for another time. Let's go and move on to this next design. Diagnostic pulse generator. In order to test some of our new manufacturing equipment, we need a pulse generator with certain requirements. However, instead of buying one, I thought we could simply create our own. For this project, you will need to make use of conditional execution. Okay, let's take a look. All right, we've got button input and a pulse output. Oh, and it looks like we've got access to a whole lot of new parts as well. That's pretty cool. We've got a note. All right, we can just type in these notes here. These are free, just for us to keep track of our logic, I guess. We have a bridge, which I'm guessing that will let you like connect signals like this. Because if you have interconnected or crossing signals, like they're going to make a junction. And sometimes you're going to need to separate your signals out. So that's what the bridge is for. It looks like we have 2 different microcontrollers available to us. We have the MC4000, which is the small one we had in the last product, and we have the MC6000. This one's a little more expensive, but we can see that we have a lot more a lot more room for code. And also looks like we have a DAT, I presume, data register as well. So this one has 2 registers. So that's pretty cool. But before we get into that, let's read the instructions here. Button is a simple input connected to a button. Pulse is a simple output connected to a device. When the button is pushed, generate pulses as indicated in the verification tab until the button is released. Okay, so when the button is high, then we generate these pulses. When the button signal is low, we do not pulse. Okay, interesting. Let's start with a simple microcontroller here. Let's go ahead and connect up our button to the input and our pulse to the output. We have to use these P0 and P1 IO slots because these are the simple IO. And it looks like we're going to have to use some conditional logic here. So let's go back up to our manual and let's see about conditional logic. Test instructions. For more information on conditional execution and the plus or minus symbol, see conditional execution page 2. Okay, let's go to page 2. All instructions in the program MC programming language are capable of conditional execution. Oh, that's interesting. All instructions. Prefixing an instruction with a plus or minus symbol will cause that instruction to be enabled or disabled by test instructions. When an instruction is disabled, it will be skipped and will not consume power. Instructions with no prefix are never disabled and always execute normally. All conditional instructions start in a disabled state. A test instruction must be executed to enable conditional instructions. Interesting. Okay, so let's look at the test instructions here. TEQ, test if the value of the first operand is equal to the value of the second operand. Okay, so test equality. Okay, so we have a little logic chart here. If A is equal to B, then it will enable the positive instructions and disable the negative instructions, and vice versa. TGT. Test greater than, test less than, and test compare. Interesting. So this is kind of has multiple logic here. So, oh, interesting. If it's equal, we have no output. If A is less, then the minus is enabled. If A is greater, then the plus is enabled. Okay, well, we should be able to just do it with the test equal here. So let's go back to Shenzhen. And it looks like when the button is pressed, we're going to have a value of 100. So what we can probably do is test equal to P0 100. So that will test if the button is pressed. If it is pressed, so we need to use the positive marker now. So if this previous test instruction was positive or successful, then what do we want to do? Then we want to start doing the pulses. So then we would move, so 100, yeah, move 100 to P0 or P1. Then we sleep 1 and then move 0 to P1 and sleep 1. Sleep 1. Okay. If not, if it's not pressed, we just want to sleep 1. Okay, so we could probably consolidate this then, because the last thing, no matter what, is going to be to sleep for 1. So why don't we do just sleep 1 there? Okay, let's see what happens when we step through this. So first thing we do is test equality. The button is not pressed, so we just sleep. We test it again. Is the button pressed? No. Sleep again. Nope, nothing yet. Okay, so now the button should be getting pressed. And now it goes into this next block of instructions. So now it should go to 100, sleep for 1, and go to 0 and sleep for 1. Now we test again for the button. Is the button pressed? Yes. Okay, we go 100, and we go to 0. Keep repeating. So far, so good. Now we're testing, is the button pressed? Not anymore, so we keep sleeping. All right, that seems like it's working so far. Let's go ahead and keep stepping through here. Looks right. All right, let's simulate it. All right, I think we got this. Cool. All right. Well, I think that's going to do it for this session. I'm really enjoying the game so far. I think it's pretty interesting. And the assembly language that they've created for this game is pretty realistic. Like, it reminds me a lot of ARM. I did ARM and MIPS are the two assembly languages I used when I was in college, and this reminds me a lot of those. So I'm liking it so far. This is kind of funny how you're an underpaid worker in Shenzhen, China, making cheap electronics. It's a pretty neat premise for the game. So I'm looking forward to trying the rest of it out. Thanks for sticking along.